Okay, let's solve one problem to begin with. Assume there is a semicircular ring, okay, which is basically a half ring. Of mass m and radius r. You have to derive the gravitational field produced by this ring at its own center. Okay, now this is not a complete ring, so you can't use the formula we derived for the field produced by a complete ring. Okay, that won't be helpful. So you will have to solve it from the basics itself. You have to consider an element of this ring, find out or not find out, write an expression for how much field the element creates at the center. Then you visualize fields created by the other elements and integrate individual fields to get the net field. Okay, try this all of you. I'll give you 2 minutes. After that, we'll discuss the solution. Think of how you are going to solve this. Your aim is to derive the gravitational field at the center. Okay, so start writing expressions. First, I'll write the hints here. First, consider an element. Next, write an expression for field produced by that element at the center. Next, visualize fields of all elements. Using symmetry, if any. Okay, if there is symmetry in the field distribution, using symmetry, determine the direction of net field. Okay, E stands for field, gravitational field. And once you know the direction of net field, write the component of individual fields in that direction. And then you have to integrate those components to get the net field in that direction. These are the steps. Okay, try to complete as many of these as possible. We'll discuss the solution after 2 minutes.
Sir, we have to integrate MdE by R.
You have to integrate DEs. DE is the electric field produced by, gravitational field produced by one element, no? You integrate gravitational fields produced by all elements, you'll get the total field. Why will you do M into DE by R? Anyway, I think you took some wrong steps. Okay, listen all of you. The first thing to do in any such problem is draw some reference lines. Let's assume the point where you are asked to find out the field is the origin. Okay, and let's take X and Y axis like this. This will help us in visualizing the directions and all easily. Now choose a random element. I'll take this one from here to here. Now this element will have a mass dm. This mass dm will produce some gravitational field at the center. Can one of you tell me the formula for gravitational field produced by a point mass at a certain distance from it? Field produced by a point mass.
So G dm by r square.
Okay, gm by r square. If the mass is dm, g dm by square of the distance. Okay, so considering element is done. Next part is field produced by this element. That will be g mass of the element divided by square of distance from element to the point where you want the field. We want the field at the center of the ring. So distance is r, radius, and you square it. That's the field produced by one element. Next, we have to visualize fields produced by all elements. Why? Because for net field, we need to integrate all the fields. Okay. Now we considered one element, the field produced by it is towards itself. You take another element, maybe this one, which lies on the x-axis. This element's gravitational field at the center will be along the x-axis itself, this way. Magnitude-wise, it will be the same. Okay, so I should draw a vector of the same length. Why? Because the mass is dm, the distance is still radius r. So the same amount of field will be produced even by the blue element. Okay. Then you can take another one on the lower side. Let's take one which is exactly below the dm that we have already considered. Let's take an element here. Okay, we need to make use of symmetry. The x-axis is a line of symmetry here. Okay, now this yellow colored element, it will produce a gravitational field at the center towards itself like this. They'll they'll all be of the same strength, and you will have infinite different elemental gravitational fields like this. Okay, now why did I take that yellow element exactly below the orange one? If we take it like that, you will be able to visualize that their y components, okay, the y components of their fields are going to cancel out. Or you can even think of it this way. See, if you consider fields of all the elements, basically you will be getting a bunch of vectors like this. One this way, and so on. Okay, infinite number of vectors distributed in this region. All of them have the same strength. Fine. And number of vectors on the upper side is same as number of vectors on the lower side. Can any of you guess the direction of resultant of all these vectors? They all have the same strength, and you know how they are distributed. What is going to be the direction of resultant of all these vectors?
Minus I.
Minus I cap. Vanilla, what were you saying?
The negative x direction.
Negative x direction. Yeah, that is correct. Okay, because the x-axis is the line of symmetry. No, whenever there are two vectors of same magnitude, okay, their resultant will be along the line of symmetry. Now here there are infinite number of vectors, but the number of vectors on the upper side is same as number of vectors on the lower side, and they are all of the same strength. Therefore, the resultant of all these vectors is going to be to the left. That's the direction of net field. We can justify it like this. Look at that orange elements field. It will have a y component this way. The yellow elements field will have an equal y component in the opposite direction. They'll cancel. But their x components, if you see, they are going to get added up. Orange one's x component is to the left. Yellow one's x component is also to the left. Every element's field's x component will be to the left. Okay, except these extreme ones, the black ones. Okay. Their y components will get cancelled. X components will all get added up. Okay. So visualizing DEs of all elements is done. Using symmetry, determine the direction of net field. That is also done. Net field will be in the negative x direction. So you don't have to integrate the complete gravitational field produced by each element. You only have to integrate the x components of fields produced by each element. Okay. Let us see how to take the x component now. Of course, to take component, you need the angle made by the vector with x-axis. So let's consider only that orange element. Just a moment. Okay, reference line is needed. This is the field produced by one of the elements, and we need the x component of that field. Okay, to derive the x component, you will have to know this angle. Let's call it theta. And you can visualize that from element to element, that angle theta is going to change. Okay, so dE was g dm by r square. Then dE's x component will be dE cos theta. I'm taking theta with the x-axis. You can take angle with y-axis also. Then you'll have to adjust the component accordingly. Okay, let me do it that way also simultaneously. How do I do that? Let me call the angle with y-axis as alpha. So if I want dE is x component, I can take it as dE cos theta. I can also take it as dE sin alpha. Alpha is with y-axis, no? So y component will be cos alpha. X component will be sin alpha. I can take it like that also. Okay. Next, we need to integrate this. We need to integrate the x components of all the fields. So net field in the x direction will be integral of small fields in the x direction. So you will have to integrate g dm by r square into cos theta. Now g and r square are constants. You can put it outside the integral. But how will you integrate dm cos theta? Theta is a variable. For alpha is also a variable. From element to element, that angle is going to change. Okay. In fact, for the topmost element, this one, theta will be 90 degrees. For the bottommost element, this one, we are taking theta with x-axis, no? For the bottommost element, theta will be minus 90 degrees. Okay. In one sense, if you are calling angle positive, in the opposite sense, you are supposed to call it negative. So these are the limits for theta. If you are writing the integral in terms of theta, limits will be from minus 90 to plus 90. If you are taking integral in terms of alpha, for the topmost element, alpha will be 0. For the bottommost element, alpha is with y-axis, no? It will be 180 degrees. So in terms of alpha, these will be the limits. We'll stick to theta first. Okay. So theta is a variable. We can't put it outside the integral. But integration is with respect to mass, integral dm. So you can't do this. Variable is theta. You're trying to integrate with respect to mass. This cannot be done. So what should we do? We should express dm in terms of d theta. Okay. Can any of you give an idea how to express dm in terms of d theta? Or what is d theta first of all? Let us visualize that. Every element of the ring subtends a small angle at the center. You can imagine it like this. We had done this in center of mass moment of inertia derivations already. If you connect the ends of the element to the center of the ring or semicircular ring, it will be subtending a small angle. This small angle is d theta. This angle with x-axis is theta, and the angle corresponding to that element or angle subtended by that element is d theta. How to express mass of the element in terms of angle subtended by the element? Any ideas?
So we can write dm equal to lambda into length of the small part.
Element. Okay, good. See, our semicircular ring is a linear mass distribution. And in linear mass distributions, if you want to express the mass of an element, you can do it this way. You can write dm is equal to lambda, that is linear mass density, total mass by total length or small mass by small length, multiplied with length of the element. That's one way to proceed. Let us do it this way first. So we are going to consider length of this element as dl. Mass is dm, length is dl. Okay. dm is lambda dl, but here we got we got dm in terms of dl. That is not our aim. We want dm in terms of d theta. So we need some more substitution. You need to relate length of this element dl to the angle subtended by the element d theta. Now that element is in the shape of an arc. It's a very small arc whose length is dl, and the angle made by the arc at the center is d theta. And we know how length of an arc and the angle subtended by it are related. L is equal to r theta, or you can write dl is equal to small length is equal to r into small angle d theta. That is how you get mass in terms of d theta. Therefore, dm is lambda r d theta. Now, what is lambda? Mass per unit length. We took mass of this semicircular ring as m. And what is the length of a semicircle? Pi r. So that is lambda multiplied with r d theta. R gets cancelled. You get dm is equal to m into d theta by pi. So this is when you try to express mass in terms of length. And there's nothing wrong in doing that. That is the way you are supposed to proceed. It's a linear mass distribution. So mass of an element will be lambda into length of the element. That is what we have used. But there is another idea also you can use. The total mass m of the ring is spread over an angle of 180 degrees, means pi radians. Okay. total mass is spread over an angle of pi radians, how much mass will be spread over an angle of d theta radians is what we want. Okay, so you can relate mass to angle also. Total mass by total angle is equal to small mass by the small angle subtended by it. This way also you will get dm is equal to m d theta divided by pi, which is the same we got by writing mass in terms of length. Okay, so there are two ways you can do it. This is much easier. In terms of angle, it is much easier. Okay, so we are now in a position to substitute dm in terms of d theta, then we can integrate also. Therefore, the net gravitational field that we are looking for, g by r square integral cos theta dm. dm is going to be written as m d theta by pi. M and pi are constant, we'll put it outside the integral. So that becomes gm by pi r square integral cos theta d theta. Okay. What about the limits? I told you that already. Sorry. If you're integrating in terms of theta, limits will be from minus pi by 2 to plus pi by 2. Angles upward of x-axis are taken positive, angles downward of x-axis will be taken negative. So to cover the entire ring, you should go from minus 90 to plus 90. So limits from minus pi by 2 to plus pi by 2. Okay. One of you quickly tell me, what is integral cos theta d theta?
Sin theta.
Sin theta, correct. So gm by pi r square, integration is sin theta, and in that we have to substitute limits minus 90 degrees to plus 90 degrees. If you do that, substitute upper limit first, sin 90 degrees is 1, minus of, substitute lower limit, sin minus 90 is minus 1. So that becomes 2. So the answer is 2 gm by pi r square. Okay. So the net gravitational field produced by a semicircular ring at its center is 2 gm by pi r square. You don't have to remember this result, but the approach is what you need to remember. How are we doing this? Okay. Since it's a semicircular ring, you can treat it as a collection of elements, particles, point masses. We wrote the expression for field produced by one point mass. Then we visualize the direction of net field. Okay. Once you consider all the fields, you can visualize the direction of net field. It will be in the x-axis. So whatever expression you wrote for field produced by one mass, take its x component and integrate that x component. With proper limits, you will be summing up the x components of all fields, then you will get the net field. That's the idea. Okay. So last class we derived the gravitational field on the axis of a full ring. Now we got field at the center of a half ring. That's fine. Next, as I said, we have to discuss the gravitational field produced by a hollow sphere and a solid sphere. So first, hollow sphere which has uniform mass distribution, means mass is spread in the same manner all over the sphere. Let's say mass is m, radius is r. As I said, we are not going to derive this result. We'll directly use the result now in 12th class chapter electrostatics. Okay. We will derive electric field produced by a hollow sphere. Okay. There we have an easier method. You'll learn something called Gauss law. Using Gauss law, you'll be easily able to derive the field produced by a hollow sphere and a solid sphere also, both inside the sphere as well as outside. Okay. Just a moment. Okay. You can consider a hollow sphere like a bubble. See, it could be made of material, metal, could be made of anything. Fine. The mass is m, its radius is r, and hollow sphere means mass is distributed only on the surface. It's an aerial distribution. Okay. Now, when it comes to spheres, the formula for gravitational field that they create will be different when you want field inside the sphere and when you want field outside the sphere. Okay. But it's very easy to remember. Suppose you want to know how much field this sphere creates at a point outside. Gravitational field outside a sphere, if the sphere is uniformly distributed, what you can do is you can consider the sphere as a single particle placed at its center of mass. In case of spheres, this can be done. Okay, proper proof you will learn in 12th class. Why or how this can be done in case of spheres, you learn in 12th class. So assume all the mass m is present at the center of the sphere and the distance is x to that point. X is the distance from where to where? From the center to the point where you want the field. Okay. So the field there will be same as that of a point mass, which is gm by x square. So the formula for gravitational field produced by a hollow sphere, uniform hollow sphere, anywhere outside it, on the surface or outside the surface, is gm by x square, where m is the mass of the hollow sphere, x is the distance of the point all the way from the center of the hollow sphere. Okay. So you just remember, if you want the field at a point outside a hollow sphere, the hollow sphere can be treated as a point mass. That's all. Next, the gravitational field inside a hollow sphere. Again, consider a uniform hollow sphere of mass m, radius r. Can one of you tell me from symmetry, what do you think will be the net gravitational field at the center of the hollow sphere? The hollow sphere is a collection of particles. Each particle will be creating its own field at the center. Okay, for example, if you consider a small particle somewhere here, that particle will be creating a small gravitational field towards itself. You consider another particle somewhere here. This particle will be creating a gravitational field towards itself. Okay, like that. Every particle on the surface will be creating a small gravitational field towards itself. And you know that fields are vector quantities. So can any of you tell me what will be the resultant of all these vectors at the center, exactly at the center?
0, sir.
0. Correct. Because for every element, there will be an exactly opposite element whose field will cancel. Okay. Net field at the center is 0. But in case of uniform hollow sphere, it so happens that not only at the center, anywhere inside the sphere, the field is 0. Okay. You take any random point wherever you want. The net gravitational field due to the sphere is 0. So gravitational field inside a uniform hollow sphere is 0. Anywhere inside it is 0, not just at the center. Okay. So when you are outside the hollow sphere can be treated as a point mass to find out the field. But if the point is inside the hollow sphere, somewhere here, then inside the hollow sphere, the gravitational field it produces is 0. Okay, let's solve a problem based on this. Suppose there are two concentric hollow spheres. So you can assume one bubble inside another one, like this. Concentric, so their centers should be coinciding. Okay. Assume the spheres have masses and radii. One has a mass m, radius r. The other one's mass, let it be 4m, and its radius be 2r. Okay. They have a common center, concentric. Okay. And I'm going to mark some points, and you have to derive the net gravitational field at these points. So one point is here, A. Another point is here, B. And the third point you can take is here, C. Where is A? A is at a distance r by 2 from the center. Where is B? R plus r by 2. 3r by 2 from the center. So you can see B is outside the first sphere but inside the second sphere. And C is outside both of them. Let's say it is at a distance 3r from the center. So you all need to find out the net gravitational field produced by both the spheres, both the hollow spheres at these points A, B, and C. So keep this formula in mind, all of you. Once you are outside a hollow sphere, the field produced by it is gm by x square, where x is the distance to the point from the center of the sphere and m is the mass of the sphere. But when you are inside the hollow sphere, the field produced by it is 0. Okay. Using these, derive the net fields at A, B, and C. I'll give you all 3 minutes. Solve it quickly. Okay. Consider the point A first. At each of these points, we want the net gravitational field produced by both spheres. The idea is to find out the field produced by each sphere and add them as vectors. Now the point A is internal to both the spheres. The first sphere of mass m is not going to produce any field at A because it's a uniform sphere and the point is inside. The second sphere of mass 4m also is not going to produce any field at A. So the net field at A is 0. None of the spheres produces any gravitational field at A. Okay, any net gravitational field at A. Next, the position B. B is external to the first sphere but internal to the second sphere. So what will happen at B? The first sphere produces a field. And in which direction does a sphere produce field? From symmetry you can tell. Gravitational field is an attractive field, I told you, no? Sphere produces a field towards its center. Okay, I should have mentioned that before itself. The field produced by a uniform sphere will be towards the center of the sphere. Okay, once you are outside it. Fine. So at point B, only one of these spheres will be producing the field. Which one? The inner sphere will be producing the field. Okay. The point B is outside that inner sphere. What is the formula for field outside a sphere? The same formula that you use for a point mass. So what we are going to do to find out this field, we'll assume all the mass of the inner sphere is present at its center. And how far is B from the center? It's at a distance 3r by 2. Therefore, the field produced at B, okay, by the inner sphere will be gm by distance 3r by 2 squared, and that becomes 4 gm by 9r square. Only the inner sphere will produce a field at B. The outer sphere does not produce any field. So this itself will be the net field at B. Simple. Next, consider the point C. The point C is an exterior point to both the spheres. Okay. So the inner sphere will produce a field at C that will be towards its own center. Let's call it E1. The outer sphere will also produce a field at C that will be towards its own center, which is the same as the other one's center. Let's call it E2. We have to find out both fields and their resultant. Okay. Since the point is outside the spheres, both the spheres can be treated as point masses. So M can be treated as a point mass placed at the center. 4M also can be treated as a point mass placed at the center now. Okay. From M's center or 4M's center, the distance to the point C is 3r. So how much field will the sphere of mass M create there? Gm by 3r whole square. And how much field will the bigger sphere create at point C? Bigger sphere's mass is 4m and the distance from its center is 3r. Square it. That's all. And since both fields are in the same direction, it's very easy to calculate their resultant. You just have to add them. Therefore, net field at the point C will be the sum of these two. 1 plus 4, 5 gm by 9r square. Okay, so if there are multiple spheres or rings or multiple point masses, combinations of these, this is how you deal with it. You have to find out the field produced by each object separately. And then for the net field, you have to add them as vectors. That's all. Okay, so the formula for the field produced, the gravitational field produced by a hollow sphere outside it is gm by x square, just like that of a point mass. And inside the hollow sphere, the gravitational field is 0. Remember, this is true for uniform spheres. If the sphere is non-uniform, we can't guarantee whether this formula is applicable or not. For both outside and inside, we can't say. Okay. Next, the gravitational field of a uniform solid sphere. Hollow sphere has mass only on its surface. It's an areal mass distribution. Solid sphere has mass spread over its entire volume. Okay, it's a volumetric mass distribution. So let's consider something like this. Now our aim is to derive, solid sphere will try to derive. Our aim is to write expressions for the gravitational field produced by it inside as well as outside. Now, when you go outside the solid sphere, the expression for field outside will be same as that of a point mass, gm by x square. How do I justify this? Why are we why are we bothered about justification? Hollow sphere, we directly discuss the formula. Solid sphere can be considered as a collection of hollow spheres. If you know the formula for hollow sphere, then you can derive the formula for solid sphere. Okay, so let us do that. As I said, solid sphere can be considered as a collection of hollow spheres. No, so let's consider a hollow sphere like this. Okay, this does not have transparency. Fine. Fine. Treat this solid sphere as a collection of hollow spheres. Imagine one hollow sphere like this. See, on screen it looks like a circle, but you have to imagine it in 3 dimensions. And you have to consider a thick hollow sphere, right? Somewhat like this. Okay. Assume its radius is small r and its thickness is dr. Then this shell element, this hollow spherical element, will have some mass dm. Okay. The point we considered is outside the solid sphere. If it is outside the solid sphere, it will be outside this hollow sphere also. Then the small gravitational field produced by this shell there will be g dm by x square, where x is the distance all the way from the center to that point. Okay. And in which direction will this small field be? Towards the center of this shell, like this. Now, not just this shell, every shell that you take, okay, the solid sphere is a collection of many shells. Every shell that you take will create a field towards its own center, and it will create the same amount of field, g dm by x square. Therefore, the net field outside becomes integral of g dm by x square. Here x is not a variable because for any of these shells, the center is the same. So the distance from center to that point where you want the field also will be the same. So x is a fixed value, it's not a variable. So all you need to do is integrate dm, that becomes m. Therefore, the field outside a solid sphere, uniform solid sphere, is gm by x square, just like that of a point mass. Okay. Next is field inside a uniform hollow sphere, uniform solid sphere. Follow this derivation carefully, all of you. Suppose you want to know how much gravitational field is created by a uniform solid sphere at a point inside it, which is at a distance x from the center. Now, the approach will again be the same. You will have to treat the solid sphere as a collection of hollow spheres, that too thick hollow spheres. So consider one hollow sphere like this. Let's say this hollow sphere's radius is r. Thickness is dr. Okay. The solid sphere is a collection of many hollow spheres like this. Now here I have considered one of them. You can consider some more if you want. Let me take a smaller one, much smaller one. Like this. And I can take a much bigger one also. Somewhat like this. Okay, so the solid sphere is a collection of many hollow spheres like this. Now you can see that the point P where we want the gravitational field, where we want to find out the gravitational field, is external to some of these shells. Okay, I can name these shells as A, B, and C. I've considered three shell elements, right? Shell A, shell B, and shell C. For A and B, P is an external point. For C, P is an internal point. C, the shell C, cannot create a field at P because we know field produced by a uniform hollow sphere inside it is 0. So all those shells whose radii are greater than x cannot produce any field at P. Only the shells whose radii are less than x contribute to the gravitational field at P. So, sorry. So what we are going to do is consider one of those shells whose radius is less than x. See, the approach is important. Okay, that is why we spend a lot of time on these derivations. The point where we want to find out the field is somewhere here, P. We took a shell element of radius r, thickness dr. So this shell element is going to have some mass dm, and that mass will create a field at P because the point P is external to this shell. How much field will it create at P? Let's call that field as dE, some small amount of field. We can write an expression for dE. dE is the field created by a shell outside it. Once you go outside the shell, the field created by the shell is same as that of a point mass. So you can write it as G dm divided by x square, where x is the distance where you are trying to find out the field. Okay, distance from center to the point P. So that field is G dm by x square. Now you need the net field at the point P And you know that all the shells whose radii are less than x will create field at P. So if you want the total field at P, you will need to integrate g dm by x square. All the shells will create field in the same direction towards the center only. So you don't have to bother about components. And see, x is the fixed distance where you want to know the field. So you can put it outside the integral. G is gravitational constant. You can anyway put it outside. All you need to do is integrate dm. But you have to integrate dm only up to a radius x, not beyond that. Because only this mass, okay, only the mass enclosed within this radius will produce field at P. The shells beyond this radius will not produce field at P. So you have to find out how much mass is there up to that point P. Means you have to find out how much mass is there in a radius x. Total mass of the sphere is m in a radius capital R. How much mass is there in a radius x is what you need to find out. And see, solid sphere is a volumetric mass distribution. So total mass by total volume will be equal to enclosed mass. I'll write it as m enclosed. Enclosed in what? Enclosed in that radius x. Okay. Enclosed mass divided by enclosed volume. Enclosed volume will be 4 by 3 pi x cube. Okay. The volume of this sphere. This part of the sphere. That's all. 4 by 3 pi cancels. You get enclosed mass as total mass into x cube divided by r cube. And that is what is integral dm. That's all. So we have a formula for gravitational field inside a solid sphere also. And what will the formula be? The net gravitational field will be g by x square into this mass. So g by x square multiplied with mx cube by r cube. X square x cube, 1x will remain. The answer is gmx divided by r cube. Very interesting result. The gravitational field inside a solid sphere is directly proportional to the distance from the center of the sphere. Gm into x by capital R cube. M is the total mass of the sphere, R is the total radius of the sphere, but x is the distance where you want the field. And you see that the field is proportional to that distance. Okay. So gravitational field inside solid sphere is proportional to distance from the center of the sphere. Okay. Hope the derivation is clear to all of you. We are treating the solid sphere as a collection of shells. And we want the field at a point inside the solid sphere. Now that point P will be external to some of these shells. For example, to the shell A, it's an external point. To the shell B also, it's an external point. But to some shells, it will be an internal point. Those shells won't create a field at P. Only the shells for which P is external will create a field. And that is what we considered. One of those shells, how much field it creates, integrate, you will get the total field. So gm x by r cube. Okay. So we know the expression for field produced by hollow sphere inside as well as outside. And using that, we derived the expression for field produced by a solid sphere inside as well as outside. Now graphs based on these field expressions are very common. You need to know how to draw the graphs. So suppose there is a uniform hollow sphere. Unless otherwise specified, you treat it as uniform, okay? Assume its mass is m, radius is r. Okay. One of you quickly tell me, how much is the gravitational field inside a uniform hollow sphere? Inside?
0. So
0. Outside?
gm by x square.
Gm by x square. Okay. So if you are asked to plot a graph of how its gravitational field varies based on the distance. Okay. As I said, when it comes to spheres, up to the distance of radius, okay, from center up to distance radius, means from center to the surface, you will have one formula. Once you go outside the surface, you'll have another formula. You know field inside is 0. And you know field outside is gm by x square. Based on this formula, you'll have to draw the graph. Okay. So on the graph, what you're representing is the field strength on the y-axis and the distance from the center on the x-axis. Now, till the distance becomes equal to radius, means till this distance, we know the field is 0. Therefore, the graph will be along the x-axis itself. 0 gravitational field. Now, once you are on the surface or anywhere outside the surface, this is the formula that you need to follow. Gm by x square. Now, exactly on the surface, x is equal to r. So the field exactly on the surface will be gm by capital R square, because the distance to the surface is the radius. So in place of x, you will put r. Surface value will become gm by r square. Once you go outside that, x increases, field strength decreases. So exactly on the surface, the field strength is g capital M by r square. And after that, the field strength decreases. Goes like this. That is how the graph will look. So what have we plotted? We have plotted a graph of how the gravitational field varies with distance from the center of a hollow sphere. Okay. Now I want you all to do the same for a solid sphere. So we need a graph of how its field strength varies with distance from the center. And in case of solid sphere also, we know the formula for field. Field inside is given by gmx divided by r cube, and field outside is given by the formula gm divided by x square. You have to draw the graph based on the formula. So field strength on y-axis, distance from center on the x-axis. Up to distance equal to radius, the graph will have one nature. After that, the nature of the graph will change because the formula changes. Or you can say the expression for field changes. So the graph will also, the nature of graph will change. Okay, do this all of you. I'll give you all 2 minutes. Can any of you describe the nature of the graph from 0 to r first? What will the graph look like? See, we have the
It
form.
is increasing graph.
Vanilla, what did you say?
So the graph is a straight line.
Straight line. Let's see. See, the nature of the graph will depend on the equation. We have the equation here. The field is being taken on the y-axis and distance is being taken on the x-axis. So the formula is y is equal to gm by r cube into x. So it's like y is equal to some constant into x. Y is equal to mx. And if you plot the graph of this equation y equal to mx, it will be a straight line whose slope is m. So slope here is gm by r cube. And up to what distance is this equation valid? Up to x is equal to r, you can use this. So when x becomes equal to r, how much does the field become? R gets cancelled, you'll be left with gm by r square. So the field starts from 0. At the center of the sphere, it is 0. Put x as 0, the field is 0. But you put x as r, the field becomes gm by r square. So the field increases linearly. Directly proportional to x means it will increase linearly like this, up to a value of gm by r square. So exactly on the surface of the sphere, the field will be gm by r square. Okay. Once you go outside the sphere, this is the formula you are supposed to use. So it's like y is equal to some constant divided by x square. Here, when x increases, the y value will decrease. Means as distance increases, the field decreases. So outside the sphere, the graph will be same for hollow sphere and solid sphere. As x tends to infinity, the field will be tending to 0. Is this clear to all of you? Any doubt in this? We draw graphs based on the equations. Field inside the solid sphere is given by E is equal to gm by r cube multiplied with x. So it's like y is equal to m into x, some constant into x. Straight line passing through the origin. It increases up to gm by r square. After that, it decreases. So you can tell that for a solid sphere, the field is strongest on its surface. Inside it is weaker, outside also it is weaker. Exactly on the surface it is strongest. Okay. You can be asked some interesting questions based on this also. I'll give you such questions in the worksheet. Like, see, at the surface it is strongest. Inside the surface field is lesser. Outside the surface also field is lesser. You can be asked to find out something like this. At a distance of r by 2, some field will be there, right? Some field will be created. Where outside the sphere, or at what distance outside the sphere will you get the same field? Such questions can be asked, and they are very common also. Okay. So field inside the sphere you have one formula, field outside the sphere you have one formula. Just equate them. You will get to know where the same amount of field will be created. Okay, you will be given questions like this in the worksheet. Solve them later. So we have drawn graphs for gravitational field produced by uniform hollow sphere and uniform solid sphere. Okay, so let's quickly go through all the field formulas that we discussed. The gravitational field produced by a point mass at a certain distance from it is gm by x square. Point mass at a certain distance x from it, gm by x square. Direction will be towards the point mass. Next, the gravitational field produced by a ring on its axis, gma divided by r square plus a square whole power 3 by 2, where a is the distance at which you found out the field. Okay, point mass formula, ring formula, hollow sphere, solid sphere, you are supposed to remember. Next, today we discussed hollow sphere inside outside, solid sphere inside outside. Hollow sphere inside, the field is 0. Outside it's like a point mass gm by x square. Solid sphere inside, gmx by r cube. Outside it's like a point mass gm by x square. Okay. Try to solve this problem, all of you. Suppose there are 2 point masses. Now 2 points can always be connected by a straight line. Assume one of them is here, the other one is here. Let's say one is m1, the other is m2. Okay. Now both these point masses will create fields. Every point mass creates fields. Okay. Consider a point which is close, very close to the first mass. If you take a point like this, m1 will create a field there, m2 also will create a field there, but the point is very close to m1. These are point masses. Field created by point mass is given by the formula gm by x square. Lesser the distance, stronger the field. Okay, so you take a point very close to m1, m1's field there will be very strong because the point is very close. Other than vanilla, any one of you tell me, what is the direction of field produced by m1 at this point? Just the direction.
Sir, towards M2.
Gravitational field is always attractive in nature. I'm asking field produced by m1. Field produced by m1 will be towards m1, towards itself. Okay, so the first mass m1 at this point produces a very strong field towards itself. Why very strong field? Because the point is very close to the mass. Okay, position is very close to the mass. M2 also will create a field here, but its field will not be that strong because the point is far away from the mass. And in which direction will M2's field be? Towards M2. Okay, so there's one field to the left, another field to the right, and you know which field dominates. M1's field will dominate. Therefore, the net field here is to the left. Net gravitational field is to the left. Okay. Now consider a point which is very close to M2, a position which is very close to M2. Again, both particles will produce fields at this point. M1 will produce, M2 will produce. M2 produces a field towards itself like this. M2's field will be very strong this time because the point is very close to M2. And M1 also produces a field there, but it won't be that strong. Why? Because the point is far from M1. Therefore, the net field at this yellow position that we have marked will be towards M2. Because M2's field is dominating there. Is this clear to all of you? Are you all able to understand this? You can ask if you have any doubt. Okay. On the line joining two particles, very close to one particle, net field will be towards that particle. Very close to the other particle, net field will be towards that particle. But somewhere along this line, there should definitely be one position where the field produced by M1 is exactly balanced by field produced by M2. At such a position, the net field becomes 0 because these two are fields of the same strength but in opposite directions. So the net field becomes 0. That kind of a point is called a neutral point. And neutral points are very, very important in space explorations. Okay, let me just give you an example. 1 second. Now, you know, we have been sending probes, okay, from Earth to Moon, Chandrayaan 1, 2, 3, right? Other countries are also doing it. These are solid spheres, okay? Earth is considered a solid sphere. The Moon is also considered a solid sphere. Moon size much smaller than that of the Earth. Okay. Now, if you consider a point very close to the Earth's surface, the net gravitational field will be towards the center of the Earth. That is why objects close to the Earth will fall onto the Earth. But if you consider a point very close to the Moon, the net gravitational field there will be towards the Moon. Okay, you release something on the surface of the Moon, it won't fall on the Earth, it will fall on the Moon. Because Moon's gravitational field will dominate there. Okay, but somewhere along the line joining the Earth and the Moon, somewhere between them, not exactly between, but somewhere between them, there will be one position where the Moon's gravitational field strength exactly balances the Earth's gravitational field strength. That is called the neutral point. Now, why is that important? Suppose you want to send a probe, okay, some machine which does some kind of study from the Earth to the Moon. You will have to launch a rocket and all, okay. Why do we have to launch a rocket and all? Because Earth's gravity will be pulling the object downwards. To send the probe from Earth to Moon, you first have to overcome Earth's gravity. So what the rocket will have to do is, it will have to take the probe, satellite, not satellite, I should not call it satellite. Okay, that Chandrayaan, whatever module is there, okay, it will have to take the module away from the Earth towards the Moon. To take it away from Earth, it has to overcome Earth's gravity. That is where the energy of the rocket gets used up. Okay. But till when does the rocket have to spend its energy? Actually, rocket won't take it all the way. There is a very complicated process. The probe itself has something called boosters and all. Okay, the boosters will take care of that. Rocket will take it to a certain height. Okay, recently, if any of you have watched Chandrayaan landing, I think in many schools and all also they showed the rocket will take the probe to a certain height. Okay, that module that is there, it will take it to a certain height. That height will not be up to the neutral point. Okay, neutral point is actually too far. We can't expect a rocket to take it all the way till there, and it's not necessary also. So what they do is, or first of all, let's discuss why the neutral point matters. Anywhere to the left of the neutral point, Earth's gravitational field will be dominating. Anywhere to the right of the neutral point, Moon's gravitational field will be dominating. So if you want to send something to the Moon, what you need to do is you need to ensure that it crosses this neutral point. That's all. Once it crosses the neutral point and you deliver the box on the other side, Moon will automatically pull it towards itself. Okay, that is where neutral point matters. Okay, and how did they actually send Chandrayaan from Earth to the Moon? The rocket will take it to a certain height above the Earth's surface, then it will release it like this. Then what it will do, the module, whatever is there, due to Earth's gravity. Now, you know, Moon itself goes around the Earth because of gravity, right? Similarly, this module, if it is projected with a certain speed, which we will learn about in this chapter itself, okay? If it is projected with a certain speed, it will orbit the Earth like this. It will keep going around the Earth in orbit like this. Now, this module has boosters, means small rockets attached to it. What it will do, whenever the module reaches this position, let's call this position as X, it will release some gases in this direction. If gases are released in this direction, we have studied in rocket propulsion, the rocket will move in the other direction. So this module will shift its orbit this way. Okay. So when it can boost itself to go out of this orbit. So a few days later, it will be in this orbit. A few days later, it will be in this orbit. Okay. Few more days later, it will exactly reach the neutral point. After that, the Moon will start attracting it stronger than the Earth. Then the module will have a tendency to revolve around the Moon. Okay. And Moon's gravity will be pulling it. But we don't want the module to undergo crash landing onto the Moon. Okay. So we don't want it to simply undergo free fall onto the Moon. Then what will happen? The module will release gases in this direction in order to slow down. If gases are released towards right, then it will experience a force to the left, which will help it overcome Moon's force, Moon's gravitational force, and land safely. Okay. So it is very important to know where the neutral point is. Till then, we have to overcome Earth's gravity. After that, we have to slow down in order to prevent crash landing on the Moon. Okay. So yeah, let's derive this. It will take 2-3 minutes more. Suppose there are two masses M1, M2. So along the line connecting these two masses, somewhere there will definitely be one position P where their fields balance. We have to find out where that position is. Okay. In terms of what? In terms of total distance between the two masses. Let's assume the total distance between them is x. Or okay, let's assume total distance is d. And from M1 to that neutral point, let's say the distance is x. Then obviously from M2 to that neutral point, the distance will be the remaining distance, d minus x. Okay. Now what I want you all to do is write the expression for field produced by M1 at that distance and expression for field produced by M2 at that distance. Then equate these two expressions. Field produced by M1 must be equal to field produced by M2. Only then net field will become 0, no? So equate those two and derive the distance x. Answer will be in terms of M1, M2 and D, the total distance. Do this all of you, I'll give you all 2 minutes.
Yes, sir.
The distance of that position from M1 was assumed as x. So tell me, how much gravitational field will M1 produce at that position? M1 is a
G.
point mass. Continue. G?
Gm1 by x square.
Correct. Gm1 by x square. And how much field will M2 produce at that position?
Gm2 by d minus x square whole x square.
Gm2 by d minus x whole square. Okay. These are the magnitudes, and their magnitudes have to be equal. Directions are already opposite. We don't have to bother about that. Okay, just equate them. So for net field to be 0, Gm1 by x square should be equal to Gm2 by d minus x whole square. We'll have to simplify this equation. Now, one way to do it is cross multiply and simplify it. But there is x square d minus x whole square. X square gets multiplied with m2. D minus x whole square gets multiplied with m1. Then x square terms won't get cancelled. It will be a quadratic equation, very complicated. But there is an easier thing to do. Take square root on both sides. If you do that, what will you be left with? You get root m1 by x. We are converting it into a linear equation. Is equal to root m2 by d minus x. That's all. Now cross multiply. D minus x into root m1 is equal to x into root m2. Okay. Send the x root m1 to that side. You get d root m1 is equal to x times root m1 plus root m2. That's all. Therefore, x is equal to d root m1 by root m1 plus root m2 separately. Okay. What is x here? X is the distance of the neutral point from the mass m1. And we got that distance as d root m1 by root m1 plus root m2. If you see the other side distance, it will be d root m2 by root m1 plus root m2. So if you see the ratio now, it's easy to remember the ratio. Denominators are same, d is common. The ratio will be root m1 is to root m2. Ratio of square roots of the masses. And you can clearly understand that this has nothing to do with center of mass. Center of mass of 2 point masses divides the line joining them in the ratio m2 is to m1. This is nothing related to that. This is root m1 is to root m2. Okay. For the Earth-Moon system, if you see, Earth's mass is about 100 times that of Moon. Okay, close to that, not exactly. Okay, let's take 81 times. That's, I think, a much better number. So let's say Earth's mass is 81 m when the Moon's mass is m. So mass ratio is 81 is to 1. So this is m1, this is m2. Now if you take root m1 is to root m2, root 81 is 9, root 1 is 1. So the distance between, or distance of the neutral point between the Earth and the Moon will be in the ratio 9 is to 1. So from Earth it is 9 times, from Moon it is 1 time. Now what's the total distance between Earth and Moon? About 4 lakh kilometers. So that 4 lakh kilometers has to be split in the ratio 9 is to 1. Means 36 lakh on this side. What am I saying? 3.6 lakh on this side and 0.4 lakh on the other side. So up to that distance of 3.6 lakh kilometers, Earth's gravity will be attracting the probe module, whatever you want to call it. After that only the Moon's gravity will dominate. Okay. So remember, the neutral point between two masses m1 and m2 divides the line joining them in the ratio root m1 is to root m2. So if you know the masses, you can tell the ratio in which it splits the distance between them. Okay, we'll stop it here for today. So this is all about gravitational field. Tomorrow you'll get a worksheet based on this, solve them. And next class, which will be on Monday, we will discuss work done by gravitational force. And from that, we will derive a formula for gravitational potential energy. Now, in the earlier chapters, we had already used mgh for gravitational potential energy. But mgh is valid only when acceleration due to gravity is uniform. But in this chapter, we are studying the basic nature of the force of gravitation. Okay. And we see that at different distances from a mass, the gravitational force is different. Till now, till system of particles, in all the chapters, we assumed weight of an object to be constant. The gravitational force acting on an object, we always used to take it as mg, fixed force. But here we are studying how it varies based on the distance. Okay. So we'll have a new expression for gravitational potential energy, all those things. And then energy conservation based problems also we'll discuss. Okay, thank you all. We'll continue on Monday. But make sure you solve and send the answers to the worksheet. Yesterday's worksheet only Vanilla has sent. Tomorrow I'll send you another worksheet. Yesterday's and tomorrow's, all of you have to send the answers. Okay, you'll have Sunday. So sit and work on it. Okay, thank you all. We'll continue on Monday.
Thank you.